Hello, good evening.
Hello. The sector of nanotechnology at present has evolved with a gigantic breakthrough in the world of technology, as quoted by the eminent computer scientist Ralph Merck. Nanotechnology will let us build computers that are incredibly powerful. We will have more power in the volume of a sugar cube than exists in the entire world today. Good evening, all. Myself, Aaron Clarence, on behalf of ASME GECBH. Let me welcome you all to the much informative and intriguing session of Introduction to Nanotechnology. To handle this amazing session, we have Mr. Arjun B S with us. He is an alumni from the Department of Mechanical Engineering from Barton Hill and a Ph.D. scholar at IISC Bangalore. His field of research is mainly focused on bioengineering and biomedical engineering. He was a recipient of a Prime Minister's Research Fellowship in 2020. Yes, you guys have heard it right. We have got a very apt person to handle our session. Without any further delay, let me welcome our Arjun sir to take over the session. Hope you all remain active throughout the session, and I request you all to keep your mic muted and videos off. In case of any query, you can unmute and speak or type on the chat box. Feedback form will be provided in the chat box at the end of the session. Please do not forget to fill it. I once again welcome you all. Over to you, sir.
Hello, everyone. Am I audible?
Yes, sir.
Yeah. Okay. You need not call me sir because I was a student like you, and I'm still a student. Maybe 3 years, 4 years, I think, since I passed out of the college. Okay. So, yeah, thank you for the introduction. Aaron, right? Aaron had introduced me, saying, and today we'll be discussing on nanotechnology and its usefulness or applications. So let me get into the topic. Okay, so in today's session, we will go, I think most of you are bachelor students or doing BTech in probably in GCBH itself. So although I'm asked to talk about nanotechnology, I'm actually taking a stop. Okay, we all know that different scales, like we commonly use this scale, right? 15 centimeter scale, 1 meter scale, etc. So which has the units of millimeters, centimeters, etc. And we know the units of meters, kilometers, etc. So these are all on the higher side. Okay, and when we go on a sub-millimeter level, we travel from, like, say, sub-meter level, we travel from meter to millimeter to microns to nanometer. So that's the way the scale works. So as much as there is a scale that goes beyond meter, like 10 power 3 times or 1,000 times that of a meter is a kilometer, and further it goes upwards, there is also a scale that goes far beyond, far smaller. That is where is the micro scale as well as nano scale. So in this section, we will actually divide into 2 stages. Why? Because a transition directly from the scale that we are usually, introduced to, or the scale of meters, in the range of meters and centimeters and millimeters. When we directly go to the nanometer, it's actually a little difficult to visualize the things. So we will take a pit stop at micro scale. Okay, so which is where I usually work with. So most of my work as well as my research work involves development of sensors and systems at micro scale. And further down is the nanoscale that we will discuss in the session further down. Okay, so you can see a few images here, and most of these things you are already familiar with. We have a watermelon that can have a diameter of somewhere around 10 centimeter to maybe around 20 centimeter. And we have far on the left side to the extreme, you can see a water molecule of diameter around 0.1 nanometer. So the atoms and molecules, a few atom, like 2-3 atom molecules are usually in the size of a few angstroms. Angstrom is 1/10th of a nanometer, or 10 power minus 10 meters. So in that range that's the range in which atoms and small molecules exist. And from there we build upon this. So each atom by atom, when they join together, we come to the bigger scales as we can see with our naked eye. Like our hair is of a diameter of around 100 micrometer. So you can imagine the scale that we are looking at. Now, anybody know who this guy is? Anybody? Okay, so this person here is Richard Feynman, a very famous physicist, and he writes actually incredible books too. And you could actually, fetch them and read them. Very informative as well as very funny. So this guy, Richard Feynman, quoted that there's plenty of room at the bottom. What he meant by this is, I think he coined this statement in around 1959, where, what he was referring to is, if we are somehow, think about it, it's 1959, it's way before, the kind of technologies that we have now. So we cannot visualize something at that scale. But at that point, he coined the term, he envisaged that if we are able to, write down something in the tip of a pin, okay, or a needle, you will be able to store the data of around 25,000 encyclopedias in the tip of the needle. So how he meant that is, if we are able to use the possibilities of using atomic level inscription kind of technologies, we will be able to store plenty of data, which is what we are actually kind of doing now when we talk about the 7 nanometer technology, 5 nanometer technology. It's all actually this. So we have reduced the size of all this computation and computers and transistors, or packing billions of transistors into a millimeter of area. We are actually doing something like that. So that's where we have the concept of tiny machines. So at that point, this is just a concept where you can build a smaller machine using a larger machine, and that smaller machine can make further smaller machines. So by going, cycle by cycle, you can actually come to a size that's very small. But this is just a concept. Right now, we do not directly do this kind of things to make smaller devices, but we employ technologies which actually directly convert something very big to a very, very extremely small in nanometers of range. We don't have multiple steps like this where something big makes something small, then further it's not like that. We have technologies that can directly convert things. Now, so on the left side top, you can see a plane that could have been used during the World War and stuff. And on the right side, you can see a supersonic jet. So can you tell me what are the difference between these two? I mean, ASME, right? Mechanical engineers. At least some of you might have taken my, talk maybe last year. I had similar slides where I discussed MEMS in general. Okay, so what I wanted to tell here is, see, we had airplanes or aircrafts that work based on propeller technology or turboprops and other technologies, which basically involves a propeller rotating at very high speed in order to create the thrust, and which basically flies the aircraft. But you have seen, the passenger aircrafts and all those aircrafts have similar kind of technologies. But we don't see a passenger aircraft that flies, more than the speed of sound. It's mainly because the governing principles, or basically when you cross the sound barrier, it doesn't work the way it used to be, lesser than the sound barrier. It's the same concept. Unless you have a technology that, that supports speeds greater than that of sound, you cannot actually use it in a versatile way. So similar to that, technologies that when we talk about, in nanometers and micrometers, these materials as well as devices in the nanometer and micrometer scales doesn't actually follow all the physics or follow the general governing principles that are exhibited by the larger scale objects. Okay, we have a lot of interactions and phenomena that happen at the micro and nano scale, which are very difficult to control too. For example, say we can see we keep something on the table and leave it for some days, and we can see that a lot of particles and dust will be accumulated over something. Say we keep a disk, okay, and finally dust will be accumulated on top of it. So, okay, what we will do, or we will take a cloth, make it wet, we will just wipe it, and we can finally see that okay, most of the dust has gone from the surface of the plate. However, if you observe under a microscope, you can see that there are thousands of dust particles that were absent or that could not be seen by the naked eye still there. So, okay, why didn't it go? It's mainly because those particles are actually belonging to the micrometers and nanometer scales. These particles will basically, interact to the surface of the plate at a atomic level, which actually makes it very difficult to remove. Or the stiction forces that this dust particle experiences by the attraction towards the plate is far large than the force that we apply to remove it from the surface. So there are so many other phenomena that happen at this kind of scales. So now we are going to start discussing about the micro scale. So I will try to quickly go through the micro scale because I have covered this earlier in another talk addressing our own students from GECBH. And main reason is we have to discuss more about nanotechnology in this section. So when we talk about microtechnology or the technologies that are in the range of microns, the main important thing that we have to discuss is about silicon. Silicon is one material that is so versatile and so useful that like all the electronic devices that we see. Why our computer is so fast with half the size of the computers before, or why is a mobile phone so fast? Why? How can you play high-end games in the mobile phones without producing so much heat? It's all because of silicon and the processes that we can use to modify silicon. So this is the basic silicon manufacturing process where it follows a basic crystallization kind of technology. As you can see in the glass, it's basically a sugar crystal. Right? Any doubt? Okay. So you can stop me in between, ask anything. I don't mind. Okay. So that we can have an interactive section. Please feel free to ask in between. Okay. So in the glass, what you see is a sugar crystal. So this basically happens due to the supersaturation. We might have studied this in the schools. The same technology is used to fabricate silicon wafers, which are extremely pure. It's said that the silicon wafers can be produced to 9 nines or 99 point followed by 7 nines. That kind of percentage purity of silicon. So such a pure form of material can be extracted with the help of silicon can be extracted in that kind of a purity. Okay, then on the silicon wafers, using the process called lithography, we actually fabricate the devices. So basically, it's like, it's always a simple process that actually repeats multiple times. Okay, so say consider that we have a silicon wafer. We can basically do two operations, an addition process or a subtraction process. So basically, what do you mean by a addition process is that, you can add material on top of something. That is an addition process. And a subtraction process is where you remove a material from a bulk material, like from the silicon. Okay. We do milling, drilling, all those things are subtractive process, right? While electroplating and other kind of technologies are additive process. Similarly, on a micro scale, what we can do is we can make or add thin films one by one or layer by layer. And, we remove them, we modify them in order to build something like a transistor or a MEMS-based device. MEMS is MicroElectroMechanical Systems. We'll come into that. So many kind of technologies are there. So let me say an example so that you will get what I'm trying to say. Okay, this substrate here is the silicon, and you can deposit something like a thin film. So say we deposit gold using some method, it's a E-beam evaporation, sputtering, or any methods. E-beam evaporation is basically where you hit you direct an electron beam onto, say, if we want to deposit gold, we will have a crucible with gold in it, and you direct an electron beam onto this gold. So it applies a lot of energy that this gold actually gets evaporated, and this evaporated gold gets adhered onto the silicon wafer. So we will get a thin film. In sputtering, what we do is we bombard gold, the same gold, with argon or some other inert gas ions, and due to this bombardment at very high energy, the gold atoms are just scattered, and the scattered ions get adhered onto the scattered atoms get adhered onto the silicon wafer, and then also we get the thin film. Then what we do to process this thin film, we apply something known as photoresist. So this photoresist is like a thin film of polymer which we spin coat or coat like a painting only. We coat it over the substrate, and then we keep a mask on top of it. Okay, you can see the black mark here. So this is a mask. So what happens is when we shine UV light, this mask or the black area will not allow light to pass through it. Okay, like a mask that Batman wears. It's like the same thing. You can only see the mouth, okay, and the eyes. So it's similar method only. So the mask will have this black region where the light cannot pass through. So once the light passes through, okay, this photoresist has the behavior that wherever the UV touches or the light touches, it will become soft and can be removed. So in the next step, you can see after development and hard baking, what you see is that, okay, the region of photoresist that was covered by the mask is retained. Now you dip the substrate with thin film, and over which we have the, the photoresist, or we will dip it into an etchant, and this etchant will basically remove the thin film. So it could be aqua regia if we want to remove gold. So finally what we have is, once we strip off the resist, what we have a substrate or silicon with a gold pattern that we need on top of it. So this process is repeated. So this is an addition process. So if you want to add something more on top of it, same process, repeat. So finally you will get a device. Okay. So this is the same process that I told you. So we can have multiple layers. Okay. So this is the photoresist. The green color is the photoresist. Then you have kept the mask. You shine the light. So once you develop it, okay. So here the resist used is another type of resist where the light doesn't get where the light doesn't touch becomes soft. So there are different type of photoresist, like positive photoresist, negative photoresist. I'm not confusing you. So let it be the some property of photoresist. Okay. So now they have shown here negative photoresist, positive photoresist. What's the effect? Okay. Now you can do multiple steps and finally get the pattern out of it. This is the basic process of photolithography. So using this kind of technology, we fabricate different things, ICs and transistors. All those things are fabricated at a very nanometer kind of scale these days, using say 5 nanometer, 7 nanometer, 14 nanometer technologies. And those are itself by a topic that we can discuss maybe some other time. And there are MEMS devices, MicroElectroMechanical Systems, where you can see here on the left hand side top is a micro battery. Okay, so a battery that is made at micrometer scale. So consider the scale bar here, that is 200 micrometers. So you can expect this battery to be within the size of 1 millimeter by 1 millimeter, which is actually very small. See, like we can use this to power a lot of small devices, like very small drones, and all those things can be powered by this kind of batteries. Then we have pumps. See, think about it. Like we have a 300 micrometer channel, okay, and we have pumps there. So these wheels, it's like a vein pump. When it rotates, the water or some fluid that we want to pump can be pumped through this channel. So if we need to meter out, say, some microliters or nanoliters of some fluid, this kind of devices can be used. So MEMS finds immense applications in biomedical as well as a lot of other fields. Even these kind of devices are used as ion thrusters in spaceships. MEMS-based propulsion systems are used in spaceship these days. We can make them in very small dimensions. They are lightweight. They are very much durable. So many other things are there. Then on the right extreme, you can see is a motor, MEMS-based motor that works based on electrostatic, or I think this is an electrostatic motor. So many different applications are there for this kind of devices. Okay, then we have accelerometers. So all the modern cars have airbags as part of their safety regulations, right? So how the airbag is deployed at almost an instantaneous, as soon as the car hits somewhere, we have to deploy the airbag so that the person will be safe. It's not like the car entirely damages and then the airbag comes out. There's no purpose to it. So how this happens is almost instantaneously we have to sense the collision and deploy the airbag. For that, we use something called as an accelerometer. You can see as soon as it hits, the airbag is deployed so that the person will be safe. So what happens there is a MEMS-based, one second. Am I audible? Can someone confirm?
Yes, you are.
Okay, great. Okay, so what you can see here is the actual working of a MEMS-based capacitive accelerometer. Okay, that's what you are seeing here. Okay, you can see that it's vibrating. There's a proof mass that is actually vibrating. Okay, that can be used to sense the acceleration by means of capacitance. Basically, what changes is this area as well as distance, right? So this basically changes, and which in turn changes the capacitance, and this capacitance is measured to, measure the acceleration. Okay. Now, why this is important is that, see, around 20 years before or 30 years before also we had accelerometers. Okay. And one on the left, the figure on the left is actually the accelerometer of this maybe 5 years here and there, while this was maybe around 10 years, 20 years, 30 years before. You can see the dimensions that we are looking at. That accelerometer for safety applications in the previous era was somewhere around 175 mm by 175 mm by 175 mm, while now it's reduced to around less than 6 mm, including the packaging. Also, the voltage requirement is less, the power requirement is less, the weight is significantly less, and the operating temperature and other things is far more superior. So basically, we are using a micro technology in order to, totally phase out an older technology, and has so many important applications. Similar technology is what we have in micromirrors. We use the current technology of projectors uses micromirrors, where each individual square that you see are mirrors, and these mirrors can be individually turned. As you can see it is inclined. So once the light from a source actually comes and hits the micromirror, you can actually actuate it. So this is basically a sink, or where the light gets lost. So this is the out of the projector. So basically, by actuating this micromirror at very high speeds, and when we have an array of micromirrors, you can have a very high HD projector that works on very low power and having very long life. Okay. Similarly, if you have a prism to split the color into 3, and if we use micromirrors again, you can actually even change the intensity of different colors. So which is basically what is being used in the current technology. So you can adjust the intensity of RGB in order to get the kind of intensity in each pixel that we need. Then we have microfluidics, where we can mimic capillaries or blood vessels in our body and see how the blood flows and how the nutritions and other things are absorbed and transferred through the body. So this is kind of a microcapillary channel or microfluidic channel, which can be used as a lab on a chip. Lab on a chip is basically a biomedical thing. Basically, what it means that you can actually make a laboratory inside a chip. So things that were earlier performed on a laboratory scale can be reduced onto a chip scale. That is what is basically meant by lab on a chip. All these things are possible with the help of MEMS or microtechnology. Okay. So this is something called as microfluidics. We'll skip that part. And we have micro pumps, as I discussed earlier, which can be used to meter out very small quantities of fluid. Then we have wearable devices or patches. So previously these, what do you call it? There are a lot of implantable devices that we have. Like if somebody has a heart issue, to monitor it, people used to wear big patches. Or somebody has Parkinson's or Alzheimer's or essential tremor, they used to implant microelectrodes onto the brain. And then finally, we need to sense seizures or some other abnormalities, and has to do some specific, you have to do something specific so as to prevent the seizure or tremor activities. So these kind of sensors were previously used, but batteries and all those sensing methods, electronics, everything used to be bulk. So you can see actually a projection on somebody's head if they are wearing something. But these days, everything is small. It is self-powered. The device can generate energy by itself, so that we don't have to change batteries. So self-sustainable devices can be made using MEMS-based technology. Then this is more. So he's the guy who actually proposed that every 2 years there will be doubling in the number of transistors in the ICs, which is actually followed so far. And now we have billions of transistors in a millimeter area or millimeter square area. That's why we have very extremely fast computers and pen drives and solid state devices, all those things, all thanks to this kind of technologies or micro and nanotechnology, but not nanotechnology, nanofabrication per se. Okay, any doubts so far? So from here we are moving to nanotechnology. So I would just stop it so that you can ask something. Anything, people? Okay, so let's move on. So from microtechnology, we are going to nanotechnology. And why nanotechnology has gained so much interest is that it has numerous applications. I mean, in what all field, I don't know. I mean, that many applications we have. Okay, now, when we talked about microtechnology, the scale or the range that we were talking was around somewhere around 1 micrometer or maybe 0.1 micrometers to somewhere around 100 micrometers or 500 micrometers. So that was the scale that we referred to as microtechnology. And then when we further come down, we get into nanotechnology, which we play around with around 1 to 100 nanometers. Okay, so that is what we are looking in nanotechnology. So here you can see here there is something like a road here on the top. Okay, and there are a lot of yellowish structures here. So basically these are all carbon nanotubes of diameter around 0.5 to 2 nanometers, while this other one I think is a hair. So you can see or understand how different the scale is compared to this nanoparticles or nanotubes or something like that. And the main important, most of the properties of nanoparticles or nanostructures comes from the fact that they have incredibly high surface area compared to the volume. And how it happens is, see, you can see a big cube here, which has a it's a cube with side length of 1 centimeter by 1 centimeter by 1 centimeter. And you know that the total surface area is basically 6 into a square. And the volume will be a cube. So if you divide this cube into, say, 1 millimeter cube, that means 1 by 10th of the previous size, you will have actually a surface area that is 10 times more than the current size. And if you further, make it into 1 nanometer cubes, this is the surface area that we are looking at. And think about it, it's the same volume. So for the same volume, we have, I don't know, maybe around 7 times or 7 orders of magnitude more surface area. And why this surface area comes to be important is that we have studied that, okay, more the surface area, more the area of reaction. Or if we want to, let me tell you some simple example. When we put this, we have all done the experiment where we drop sodium into water, right? And the sodium basically emits hydrogen, which actually gets burned, and the sodium floats around the water. We have seen the experiments. This same experiment, if you flatten out the sodium and put it there, you could actually see probably an explosion, because large amount of reaction, the reaction is so fast because the area exposed is so much more, and so much generation of heat as well as gas is there, which actually can even cause an explosion. So, and similarly, more and more things are there in this regard. So that's why nanotechnology is getting a lot of interest, especially in biomedical field. Okay, so you can see the graph here where surface area per unit volume is plotted against the radius of the particle. So as the radius of particle decreases, there is huge increase in the surface area, of the total surface area available. The term nanotechnology was actually coined by Professor Norio Taniguchi, and he is the one actually, I think 1970 sometime he coined this term nanotechnology, but although we started making things further later. So how do you classify nanomaterials? I said, okay, what the scale that we are looking at is somewhere around maybe 1 nanometer to 100 nanometer. So how can we further classify these nanomaterials? So nanomaterials can be classified as 0-dimensional or 0D, or 1-dimensional, 2-dimensional, 3-dimensional. And what exactly means by this is that 0D is the kind of particles or nanomaterial that have dimensions. Say, if we say X, Y, and Z dimensions, okay. If the 3 dimensions of the material all belong to the nanometer range or the nanotechnology range that we talked about, like 1 nanometer to 100 nanometer. If all the 3 dimensions of the material are sticking to the one, or are in between 1 to 100 nanometer, we call that as 0D material. For example, quantum dots, fullerenes, Buckminster fullerene, you might have heard of it, which is a 60 carbon, spherical shaped football kind of thing. Okay, or gold nanoparticles. All of this have dimensions less than maybe 1 nanometers or 2 nanometers, which essentially means it's all the 3 axes. We have dimensions between 1 to 100 nanometer, and it's a 0D. While carbon nanotubes, okay, which are very popular, carbon nanotubes have a diameter of around 0.5 nanometer to around 2 nanometers, and could have a length of up to say 1 or 2 millimeter even. So of the 3 dimensions, 2 dimensions, so that across the diameter belongs to the nanometer scale, while the other dimension is in micrometer or millimeter scale. That's why it's 1D. Similarly, graphene sheets, which are actually 1 carbon atom thin, okay, those actually follow the same thing. Okay, they have dimensions in one direction, they have in nanometer scale, but in the other direction it could be bigger in micrometer scales. And this 3D materials, or then you will be wondering, okay, then why these 3D materials are called nanomaterials at all? Because okay, if all the 3 dimensions are greater than 100 nanometer, how is it becoming a nanomaterial as such? Or then it doesn't follow the rules, right? But then these 3D nanomaterials are materials which are composed of large number of smaller nanomaterials. So hence that's why they are classified as 3D material. Essentially, they are all made of large number of smaller nanoparticles or nanotubes or nanofilms. That's why they are called this. So you can see here, a liposome is basically a phospholipid elements which actually combine together to form something like this. So or a polycrystalline silicon will have a large number of nanometer level crystals which actually join together to become a polycrystalline. Okay, so how do we synthesize nanomaterials? Okay, I have already talked how we make micrometer level devices, right, or micrometer level technologies. So what we are now interested is to see or understand how we fabricate or develop nanomaterials as such. This is too small a dimension to fabricate, right? So we have 2 different approaches. One is the top-down approach and one is the bottom-up approach. So as the name suggests, the top-down approach is where we divide bigger materials in order to get smaller fragments or smaller materials until we reach the nanoscale. Or in the bottom-up approach, we assemble atom by atom, okay, and then we assemble it to the extent where we need the specific size of the nanomaterial. So both these approaches are there, and we have over the years developed technologies that can fabricate nanomaterials using either of the methods. Okay, so the synthesis or the nanoparticle synthesis can be categorized into different categories as such. Like I said, bottom up and top down. Similarly, we can actually also classify them based on the method that is being employed. So we have physical methods, we have chemical methods, and we have biological methods. In physical method, what we do is grinding, okay, or ablation or evaporation and condensation. So these kind of physical methods are used to generate nanoparticles, where in chemical method we use precursors or chemicals to say the process like pyrolysis, where you introduce a gas with specific atoms that we need to convert into nanoparticles. We will introduce a gaseous mixture or a compound, and we apply very high temperature so that the solvent in which it is dissolved and get evaporated, as well as the chemical or the compound with the specific nanomaterial that we need to synthesize gets pyrolyzed or split due to the extreme high temperature, and the required atoms get precipitated or deposited on the surface that we need to grow nanomaterials. So these are the chemical method. There are sol-gel methods and other techniques as well. Then we have biological methods too, which is totally a different ball game. We won't discuss much about that. Okay, so this is one of the mechanical process where we use, or this is a very popular as well as old technique where we use, you can see grinding balls which are shown in red color. Okay, so this is basically a top-down approach where you put in some material that we have to convert into nanoparticles along with this grinding balls, and we rotate this entire jar. So when it rotates at very high speed, this grinding balls will hit against this material, making it into smaller pieces. And these smaller pieces will again get, they will all hit with each other. Then finally, we'll get the particle sizes in the order of nanometers. However, there are, as I said, when we go to the scales of nanometers, the kind of physical forces that we are experiencing are also different. So say the material that we need are positively charged or cationic or anionic or even neutral. What happens is when we grind it, we get smaller particles. Okay. However, if we do not have something called as surfactant or something that prevents them from binding back together again, okay, they will become clumps again. And these clumps, okay, or the particle clumps or the particles, one aggregated, basically becomes of larger size, which may not be of use to us. So we use something called as surfactants, which actually prevents them from coming together. So they will remain in the size that we need. And these surfactants are designed such that we can do some chemical process or some other process in order to selectively remove them so that the nanoparticles can combine together. And once they reach some specific size that we need, say like not always we need nanoparticles of 1 nanometer size. Maybe we need something of 50 nanometer size. So we may go down to grinding to say 10 nanometer. Then we, in a controlled manner, we allow them to come back together to reach to the 50 nanometer scale. So for that, we use surfactants. Okay. Then there are other methods like inert gas condensation. So I told you regarding E-beam evaporation, right? So here also it's something similar. You can evaporate it using multiple methods. E-beam can be one method. Laser ablation can be another method. Then you can use thermal heating, which is another common method. Okay, or you can use an arc in order to create a high temperature at that point and can use it to evaporate. So in a chamber, as you can see here on the left side, we can keep the evaporation source and with the material that we need to make nanoparticle out of, and you evaporate these particles in a chamber that is filled with an inert gas, so that no reactions and oxidation and other things happen. So in this inert gas environment, and usually this happens at low pressures of around 100 Pascal or something like that. So what happens is these atoms, once evaporated, okay, there is, you can see this cooler, right? So usually liquid nitrogen or other coolant will be used to condense this evaporated material. And once it is condensed, these particles will fall down and are connected through a funnel like this. And from the collector, they are sent into this high pressure and low pressure and high pressure compaction units. So all the particles here might be in the order of some atoms, okay, a group of atoms probably, and we might not be, as I said earlier, we may not need those kind of small particles. So in compaction units, you do some processes so that they will become into the dimension that we need. Similarly, we have chemical vapor deposition, where we have, we introduce some chemical compound which has some particle. It's very commonly used for silicon, especially for CVD deposition of silicon. So we introduce a gas with silicon in it, and we make it react, and the reactant will fall on the surface onto which we need to grow it. And a lot of processes are there, like absorption, migration or diffusion, surface diffusion. All these things are there. But finally, we'll get a nanometer level film there on the surface, or nanometer level particles on top of the film. So many different methods are there. Then there is sputtering, where I said we can bombard the sputtering target in order to release the atoms of the target, and we can deposit them on the substrate or onto the material that we need to deposit upon. Then we have electrodeposition or electroplating, very controlled electroplating, which is a very bulk process that we also do right now. I mean, for bulk thin film or thick film preparations, the same technology is used. Then there is electrophoretic deposition. So many other techniques are there to synthesize nanomaterials. Okay, any doubts so far? Okay, then we have synthesized nanomaterials. Okay, now what next? So we need to understand what are the properties of nanomaterials. Okay, the graph that I have shown here is just for the mechanical properties of nanomaterials. Okay, so you can see here on the plot on the left side. Okay, so this is basically a stress strain graph of, and this coarse-grained copper is basically the copper that we see on everyday life. Okay, and you can see it is highly ductile. Okay, we can go up to say 15% strength without creating too much stress. However, if you want extremely high strength copper, what we can do is use a nanoparticle based copper material as such, which has extremely high strength. Why this happens is, say metals will have large number of grain boundaries within it, and while we develop a metal based on nanomaterials, the grain sizes are so controlled that all the grains that consist or that come together in order to form that bulk metal, the grain sizes are very small, maybe in the order of nanometers or micrometers. So what happens is, even if we introduce some stress or when we apply some deformation, the dislocation doesn't happen throughout the material. And or in the case of this coarse-grained copper, what happens is when we introduce some dislocation or defect, it actually propagates through entire length of the material, and actually it affects the strength of the material. However, in case of nanomaterials, we have very much control over the grain dimension, which actually provides this kind of copper or copper fabricated using nanotechnology to have very high strength. And so you can actually play with the size of the grains in order to get different behaviors for the same metal itself. So this nano twin copper, actually you can see here, it has extremely high strength, similar to the NC copper you have seen here. At the same time, this material have extremely high ductility also. So many, you can tweak the material in order to get different mechanical properties. Similarly, you have super paramagnetism behavior in many of the ferromagnetic nanoparticles. For example, iron, cobalt, etc. These are materials. You might know that they are ferromagnetic in nature. You apply a magnetic field and you can magnetize them. And see, there is something called as a critical diameter. Okay, so if you make nanoparticles of say iron of dimension around less than 50 nanometers and magnetize them, okay, so it is, the grain is so small that it will have very high domain behavior or very high magnetic behavior or super magnetic paramagnetic behavior. And this grain, when introduced, or this domain when introduced to a similar sized another domain, the magnetism is induced on the other one. So finally, once this gets accumulated, we get a super paramagnetic material. This can be very extremely useful. So you have to make a grain size that is less than that of the critical diameter. Then there is superconductivity. So there is an expression where we know that there will be electric conduction follows something known as energy levels. Okay, and so energy levels in case of or the energy levels of electrons. Basically, in a crude way, if I say it is proportional to say n square, or the energy level square, by the length or the lattice length along that direction squares. So what happens is at higher dimensions of in order of micrometers or meters, the energy levels are so close that a little bit of energy actually causes electrons to jump from one level to another. However, when we come to the nanometer scale, what happens is the dimension square or the L square actually comes on beneath, right? So the energy levels are spaced with huge bands of energy in between them. So at nanometer scale, what actually happens in this case is, say we have discussed about 1D material, 2D material, etc. Right? So the electrons do not have mobility. Say if we have a 1D material like carbon nanotube, what happens is the electrons doesn't have mobility in to that nanometric dimensions. So across the diameter, it doesn't have much mobility. However, along the length of the carbon nanotube, it has extremely high mobility. Okay, so this means that along the direction of along the longer direction, we have extremely high conductivity, which essentially leads to superconductivity in this kind of materials. And we can also fabricate supercapacitors, since the area that we have, like we know capacitance is given by epsilon 0 A by D. So since the surface area between, so we have carbon nanotubes which are concentric in nature. Okay, so this kind of carbon nanotubes can be used, or two thin layers of graphene can be used to develop a supercapacitor which can hold immense amount of charge between the two parallel plates. Then thermal conductivity is another property that is similar to the superconductivity. The temperature transmission in metals and crystalline materials actually is carried out by something called as phonons, similar to the electrons in case of the conductors. So the phonons are also restricted by the lattice vibrations along the nanometric dimensions. So the thermal conductivity in one direction could be extremely high. And melting point, if we come to talk about the melting point, the surface area exposed in case of a nano material, say, is very high, that the energy that we apply is actually distributed all over, and a lot of atomic bonds get broken. And in most of the cases, even for metals, the melting point of these nanoparticles will be lesser compared to that of the bulk material as such. So many different applications and properties of nanomaterials are there, and each different properties can be used for different applications. We can use this for high energy storage to develop batteries like lithium polymer and lithium ion batteries with high energy storage capacity. Then the hydrogen can be stored in between the material, so that is used. Then in the fuel cells, so many different applications are there. For example, graphene is used in batteries, okay, so that it has very fast charging as well as high capacity. Graphene has incredible mechanical strength which can be used and to fabricate supercapacitor, and So many different applications are there. Then we have carbon nanotubes and quantum dots. The carbon nanotubes, each carbon can be seen to be bonded to 3 different carbon atoms. So one electron is actually free to bond with some other material, and this behavior is used to bond with some specific biomolecules and other things for drug delivery. I will come into another slide where you will understand it better. Okay, then we have quantum dots. Quantum dots are basically 0D particles. Okay, and they, as I said regarding the energy bands, so as we go on reducing the size, the energy bands are very discrete, and energy is equal to h nu. So each energy band, basically these quantum dots, express photoluminescence behavior. So basically, when you apply energy, the light is emitted. So the same principle, you apply some UV light onto the quantum dots, they will absorb it and they will emit light of some other wavelength characteristic of their nanometric size. So you can see these bottles will have different nanoparticles of different size, and based on their size, they have different emission. So as the size reduces, the color changes from red to blue, basically. And we know that LEDs of this era are actually very highly efficient, and in the next gen, it's going to be quantum LEDs or QLEDs, which actually are way more efficient and compact. Okay, so this kind of things are there. And see, this cadmium selenide quantum dots, these are actually injected into the region where tumor is there. Okay, so this is a very wonderful technology, basically. So if you need to understand where the tumor is, the doctors actually injects this kind of quantum dots, and they so what happens is the tumor grows rapidly. So whatever nutrients and molecules that we supply in the region near to tumor, the tumor cells will absorb it. So the tumors will quickly absorb the quantum dots, while the normal regions will not. So what happens is, if you shine UV light on top of the tumor region, or the entire region where we want to observe, the tumor region where the quantum dots are absorbed will emit characteristic color, which can be used to identify the tumor location. And other applications include biosensing. Say, zinc oxide is a very thin film material which is very commonly used because of its specific chemical properties. Zinc oxide is very efficient in adsorbing and absorbing some specific biomolecules like acetone and other things. So previously we used to deposit zinc oxide using sputtering or some method that we discussed earlier, and we used to get a very thin film. Now with the advent of nanotechnology, we can actually make nanowires, which actually increases the surface area in the same overall footprint. So basically we have more surface area to react and more sensing happens. Similarly, as I said earlier, the carbon nanotubes have free electrons which can be bonded to different materials. This method, or this feature of carbon nanotubes as well as graphenes, have been used to identify or bind pathogens or heavy metals or some other molecules to detect them. And measuring the conductivity or resistivity of this kind of carbon nanotubes and materials, we will be able to detect, say, whether this pathogen is there, or the water is contaminated by this heavy metal or not. So many different applications are there. Then nanoscale drug delivery. See, one common or one important application is in case of treating brain tumors. So this is something that is of interest to me also, because it's the field of my work. So in the brain is something specific. Okay, so if a person have brain tumor and we need to treat them with chemotherapy, chemotherapy is one of the common methods used to treat tumors in different parts of the body. However, in case of brain, what happens is, when you introduce drugs that can target brain tumors, there is something called as blood-brain barrier in case of the brain. So these are the barriers that surrounds the capillaries in the brain. So what happens is these are very highly selective semi-permeable membranes, which does not allow unwanted things to get into brain. So in many cases, in the previously when people used to apply drugs, what happens is this semi-permeable membrane or the blood-brain barrier will not allow this drugs to go to the brain and kill the tumor. So recently what happens is people have developed liposomes or fullerenes or carbon nanotubes based technologies where we attach the drugs to these kind of nanoparticles and send them through the capillaries. Since these are very small particles and they are very small compared to the size of this semi-permeable membrane, they can pass through into the brain and treat the tumor. Then there are so many different applications like lab on a chip. All these things are there. And in 2016, these three people actually got Nobel Prize for developing something called as molecular machines. So machines is something that can, have some moving parts and do some efforts. And that's what this amazing scientist actually did. So the first invention was somewhere in 1983, I guess, where they made this catenane. So you can see two rings. So these are entangled rings. That's what Jean-Pierre Sauvage actually made, okay, in 1983. So one ring will have motion with respect to the another one. And then Sir J. Fraser Stoddart actually made the rotazane, where you can see the blue line, or it's like a axis, and this green color ring is actually, surrounding it. So along this axis of the blue line, or along the blue line, the circle can actually move back and forth. So basically, freedom of rotation as well as movement is there. And finally, Bernard L. Feringa, what actually he made was a nano car, where he used this nanotechnology in order to make a nano car that can move around. So these are all actually happening at very nanometric scale and cannot be visualized as such, like a moving car or something, but these are technologies that people have developed. So nanotechnology has immense potential, and we have had some glimpse of the entire thing. So that will be the end of my presentation. If anyone has some doubts, you may please shoot. I think everyone slept off. It's already night. Any doubts, anyone? No other question? Leave?
No. Since no doubt, let us move on to the conclusion.
It's like there's a lot of noise from your side. Was the session informative at least? I think most of you slept off. As simple as that. മനസ്സിലായില്ലായിരുന്നോ? Anything else you want to ask me? Like nanoparticle, nanotechnology, അല്ലാതെന്തെങ്കിലും? Regarding PhD or IISc or something? Okay, then we shall make a move.
So, good evening, all. Myself, Srirag of GEC Barton Hill. So, here we have reached the end of this wonderful session. First of all, on behalf of GEC Barton Hill and ASME, I want to express my sincere gratitude to our Arjun Jata for handling this session in such an effective manner. As a listener, the session provided me a vivid view on nanotechnology, and it also clarified some points which I had studied in the previous classes. So once again, thank you, Arjun Jata. Thank you for your time. And dear participants, hope you also have enjoyed the session and followed the session. So thank you for your cooperation, and we are expecting all of you in the upcoming events too. And that's it. Make sure that all of you have filled the feedback form. Thank you.
Okay, thank you. Bye. Good night. Have a nice day. Bye.